All right, well, we have an interesting day today. We have an impromptu cameraman, one of our students, so thanks for doing that, Kyle.
No problem.
And we don't have any homework due today, so I don't suppose there's any questions about the homework that's due Thursday?
Not yet.
Okay, all right. And last time we did some proofs by mathematical induction. And we did, first we did some equality proofs at the beginning. Then last time we did an inequality proof. So you'll have a couple of proofs of inequalities by mathematical induction for your homework assignment on Thursday. And the other thing that you have to know, that we have to know how to do, is how to do proof by mathematical induction with word problems. Now, most people don't like word problems, you know, in algebra, but so be it. So here is our first word problem proof. So here we have, this is from the book, an example of a proof by induction. So let's read the problem here. It says, consider a currency consisting of 2-cent and 5-cent coins. So everybody is familiar with a nickel, that's a 5-cent coin. Let's just imagine that there is a 2-cent coin. So we have a 5-cent coin and 2-cent coins. And that's the kind of money that we have, all right? And now it says, show that any amount above 3 cents can be represented using these coins. Any amount above 3 cents. So let me give you an example. Let's say that there's, you want 15 cents. But how could you have 15 cents with only 5-cent coins and 2-cent coins?
3 5s.
You could have 3 5s, right? How about 17 cents?
3 5s and a 2.
3 5s and a 2. But how about 16? Well, that might take
2
a little
5s and 3 2s.
No, 16. 3 5s would be 50.
2 5s and 3 2s.
Essentially, for an odd number, you just need one 5-cent coin, and everything else could be 2. And then for an even number, you just...
Is that?
Yes.
Yeah.
If it's odd, you have to have an odd number of 5 cents, and if it's even.
Yeah, but what about, it says any above 3.
Yeah.
So that would include, so starting with 4, 5, 6.
So, yeah.
If it's even, you do, for example, for 4 cents, you just use 2 cents. For 6 cents, you use 3 2 cents. And you would only use the 2-cent coins for any even number.
Okay, so it sounds like you have figured out a way in your own mind to make it work.
Mm-hmm.
What we want to do is we want to use proof by mathematical induction.
Okay.
All right, to prove this. But that's good that you've figured it out. All right. But we want to, because there are other word problems that are similar to this that have to do with various data structures, where you have to be able to reason with words and use proof by mathematical induction. So the purpose of this is to use mathematical induction to solve this problem. So here's the next paragraph here in the slide says, we write P dot N in English as P dot N. Some bag of 2-cent and 5-cent coins has the sum N. Our task is to prove that for all N greater than or equal to 4, P dot N. All right? Now, here is what's tricky about using proof by mathematical induction to prove word problems. The tricky part is to write down the problem, and in particular in the induction step, to write down what it is you have to prove, assuming what as the inductive hypothesis. Are you with me?
Mm-hmm.
Okay, so here is so our problem is how shall I write this? Consider prove any amount possible. Prove that any amount is possible with 2-cent and 5-cent coins. With 2-cent and 5-cent coins. Above 3 cents. right, so now, so that's what we have to prove. We have to prove any amount possible with 2-cent and 5-cent coins above 3 cents. All right? And now there's going to be a lot. Now to do these proofs, you're going to have to write a lot of English. All right, that's what's going to be hard about it, is writing out the, because we're so used to doing formal methods with, you know, quantification, etc., blah, 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 blah. Then this is a really different flavor, because we have to write stuff out in English with these word problems. All right. So now, how do you always do a proof by mathematical induction? What's the very first?
Base case.
Base case, exactly. So here we have base case. All right. So what do we have to prove for the base case? Base case is n equals what?
4.
No, 4.
4. Base case is n equals 4, right? So, okay, base case. So, base case n equals 4. So we have to prove that what? That 4 cents is possible. So must prove 4 cents possible. With 2-cent and 5-cent coins, right? With 2-cent and 5-cent coins. All right? Well, what's the proof? No. What's the proof of the base case? What's the proof of the base case? What do you have to write down now? What do you have to write down now for the base case? Come on, you guys. What's the next thing? We said this proof is in English. You got to write down in English. What do you have to write down in English here?
2 times 2n. Well, because you have to do the 2-cent and 5-cent coins.
We're trying to prove that any amount is possible with 2-cent and 5-cent coins.
So it would be like 2n plus 5n, or
2n plus 5n equals.
No. You're making
2k plus 5k equals n.
No. It's much easier. What we're trying to prove the base. What are we trying to prove in general? That any amount is possible with 2-cent and 5-cent coins. So what's the base case? The base case is what amount? The base case is what amount?
4.
The base case is 4.
Right.
Is an amount of 4 cents. So how do you prove that? How do you prove the base case?
You show that two 2-cent coins equals 4 cents.
That's what you say. Exactly.
Oh.
Are you with me? You demonstrate that it's true in the base case, which is with 4 cents, right? Mm-hmm. Okay, so the base case is, so must prove 4 cents possible. But how is that possible? Use what?
2 2-cent coins.
Yeah, so proof. Use 2 2-cent coins. That's 4 cents. Are you with me?
Okay.
That's the proof. That's the base case proof. Are you with me? So here's it. So use 2 2-cent coins. Okay. That's the proof for the base case. Are you with me?
Yeah.
Do you see? This is it's easy, but it's hard because
thinking in English.
We're thinking in English, right?
That's
it's
weird.
hard because we're thinking in English. Yeah, it's weird. It's hard because we're thinking in English, and that's weird for us because we're all formal methods people. And this is a little informal, a little less formal. Are you with me? But do you understand? Use 2 2-cent coins. That's the proof of the base case. We prove that it's possible, right? In the base case.
Yep.
Now, here comes, what's the next case?
Inductive case.
Induction case. All right. Now, every time we do the induction case, what do we always have to write down? We must prove blah, 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 assuming blah, 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 as the what?
Inductive hypothesis.
Now, my question is, and you must write this down. We must prove that what?
n plus 1.
Yes. Must prove that n plus 1 cents is what? Possible with what?
2-cent and 5-cent.
2-cent and 5-cent coins. Okay, must prove, quote, n plus 1 cents is possible with 2-cent and 5-cent coins. With 2 cent, that's okay, we're forged ahead.
Good.
2 cent
Thanks.
and 5-cent coins. Okay. Now doing what? Now what do we write here? Assuming, yeah, good. So assuming what?
And is it possible?
And
Cents is possible with 2 cents.
Oh.
Are you with me? You got to write that all out. Okay. Assuming, quote, N cents
Smells good.
is possible
with 2-cent and 5-cent coins.
Possible with 2 cent and 5-cent coins.
Should we just prove binary?
No, hold on. But now what do we have to say? There's another phrase.
As the inductive hypothesis.
As the inductive hypothesis. Now trust me, writing this out is hard because of the fact that we're used to doing things in formal methods, and this is a less formal. This is English reasoning, but it's the same concept. All right. Now, how are we going to do this? We are what?
Formal methods.
What? Well, no, we're not. Well, not formal. No, this is informal. We have to do this informally.
We can't prove all of them.
Well, we have to. Huh?
We use the n+1 cents to start with.
Oh, well, do we use the n+1 cents to start with, or do we use the? How? Well. No. How? Look, assuming what are we assuming? We are assuming that we have.
If we can prove 4, 5, 6, 7, 8, 9, 10, then it would repeat itself.
Actually, there are several cases that we are going to have to do a little bit of a case analysis.
Okay.
We are, and that's a good observation. But what do we have to show?
Prove 5?
No, look, hold on. Let's assume that we already have what?
N cents.
N cents.
It's approved.
And my question is, if we have n cents that is made up completely of what? Of just what?
2 cents, 5
2s
cents.
and 5s. How can we get n+1 cents?
Take away 2 2s and add 5.
But that only works if you have what?
At
More
least
than-
4.
That only works if you have what?
More than 3. 2 2s and a 5. I mean,
If you
already have 2 2s.
If you already had, yeah.
so you have to start.
That's a good
Which
observation.
means you have to have at least 4, right?
Right. So how do we formulate our reasoning there? If you have at least 2 2s, what you said is that if you have at least 2 2s,
Then you can
2 cent
take them
coins,
away,
you
and
can take away the 2s and replace it with a 5, and that's how you can get n+1 with n, and you would still only have 2s and 5s, right? Because you'd be taking away 2 2s and placing one 5s. You still have only 2s and 5s, and you have one more than you had before. But what if you don't have 2 2s? How can you not have at least 2
If you have
2s?
a 5.
If you don't have 2
you're going
2s, you
to
take
6.
away a 5 and add 3 2s.
But if you don't have 2 2s, how do you know you have a 5? Or maybe if you have a 5, how can we divide this into the? What you're saying is you can take away a 5. What did you say? Take away a 5
And add 3 2s.
and add 3 2s, and that would get you one more. So either you have what? Either you have.
A lot of 2s and a lot of 5s.
Well, yeah, what are the 2 cases? And how can we reason this? And what about? And how does this? How does this? How does this relate to the base case, which is n equals 4?
It's what Ben said. If you have an odd number, you take away a 5 and add 3 2s. If you have
how
an
do you
even
know
number,
with an odd number that you're going to have a 5?
Because it's,
you cannot get an odd number with 2s.
Oh, if you have an odd number, you have at least
1 5.
1 5.
And if you have an even number, you can get any number without a 5. But assuming
If you have an even number, you take away 2 2s and add a 5. If you have an odd number, you take away a 5 and add 3 2s.
Actually, if you have an even number, you can just use all 2. Well,
Not if
we
you
want to
have-
show that if you have n,
You
then
get n plus 1.
you get n plus 1.
Anytime it's an even number, you take away 2 2s and add a 5, and you get n plus 1.
But then there's
But how do you know that
10
there's 2?
and
How do you know
20,
that there's at least 2 2s with an even number?
4, 6, 8?
Because
all
we
those
can't go
numbers.
less than 3, and so if we have at least 4, if it's an even number, there's at least 2 2s. And then you're thinking 10 as 2 5s.
That's true. You just shot your
So
theory
you
down.
can say odd numbers and multiples of 5 if you want.
Well, yeah. What are the 2 cases? We need to figure this out. How to make this?
So are we proving?
We want
We're
to
proving that any amount is possible with 2 cents and 5 cents.
I know, but the way we are doing it is we are assuming that you have n and showing how you can get n cents and how you can get n plus 1 cents, and we need to kind of refine what the cases are
Yeah.
to make it airtight, to make our argument airtight. Are you with me? So could we do it? I think there's a couple ways to do it. We could either say there is at least 1 5-cent stamp, or 1 5-cent coin, or not. Could we reason if there's not a 5? If there's not a 5, then there has to be I think that's the way to do it. Either we have a 5-cent, or we don't.
Okay.
Are you with me?
Okay.
So.
Because that'll distinguish between odd and even numbers.
Well, no, well, it's not quite, because either having a 5 in the pot or not, because you could have for 10 you could have 2 5s, or you could have
5 2s.
5 2s. You don't know which. You don't know which. So I think the cleanest way to do it is to assume you either have a 5 in the n or you don't.
Okay.
Are you with me?
Yes.
Okay. So case. So here we'll do 2 cases. Case 1. There is at least 1 5-cent coin. You have case 1. We have n cents with at least 1 5-cent coin, right? Okay. So here, case 1. We have n cents with at least 1 5-cent coin. All right. So that we have to write this down in English as part of the proof. All right. And so now what? And so now what do we say? And how do we get n plus 1 cents out of that?
If we have a 5-cent coin, we can take it
have
away.
with at least 1 5-cent coin. So what do we do?
We can take the 5 cent away and add 3 2s.
Yes. So remove 1 5-cent coin and replace by how many? 3 2-cent coins by 3 2-cent coins, and the conclusion is that we have n plus 1 cents with only 2s and 5s.
Right.
So now we have n plus 1 cents with only 2-cent and 5-cent coins. All right? So that's our reasoning. Well, if case 1 is we have n cents with at least 1 5-cent coin, so what's the opposite of that?
None.
With no 5-cent coins. So case 2, no 5-cent coins. But now what do we have to do? No 5-cent.
We have to remove two 2-cent.
But how do we know there's 2?
Because we're starting at 4.
Ah, there's our Are you with me? Okay, so case 2, no 5-cent coins. Okay, therefore there must be only 2 cents. So okay, so therefore, we only have 2-cent coins. 2-cent coins. But the base case was what?
4.
More greater than or equal to 4.
Right.
Okay. But the proof is for greater than or equal to 4 cents, right? But the proof is for an amount greater than or equal to 4. An amount. Well, it said greater than 3. For an amount greater than 3. So we must have at least 2 2-cent coins. Now, so you see how the logic works? So we must have at least 2 2-cent coins. So now comes our thing. So now how did we, so now what do we do? Remove 2 2-cent coins and replace by
3.
1 5. Okay. So remove 2 2-cent coins and replace by 1 5. Okay, by 1 5-cent coin. Right? And now we have n plus 1 cents. So here, now we have n plus 1 cents.
With only 2 cents and 5 cents.
Yes. With only 2-cent and 5-cent coins. And these two are the only possibilities. Either you have at least one or you don't have any 5 cents, right? So that's it. Boom. Now look, you guys, this I took some time to write all this out because this is what you have to write out when you do word problems using proof by mathematical induction. You have to get the concept down and then describe it in English. This is not formal methods. This is proof by mathematical induction, but it's not, you know, formal with symbol manipulation, and there's hardly any math here at all.
Can we just write there exists, blah, blah, blah?
Yeah, you can't say there exists a sense, blah, yeah, you can't do this informally. You cannot do this formally. So some proofs have to be informal. Yeah? And this is typically the way math is done. Math proofs are done. Math proofs are done in English, traditionally. Traditionally, math proofs are not done formally like we do them. Traditionally, math proofs are done informally. And the mathematics, you write this stuff out, and it's all in sentences. It's in paragraph form, and it's all this verbiage. But then the reasoning is the same kind of reasoning that we do formally. They do what we do formally. They do it informally. But then you have all this reasoning that you have to keep track of, and you have to write it all out in English. It's harder. Now, formal methods is much easier and more concise, and you can see exactly why each step. But can you imagine if we had done all of our set stuff, set theory, this way in English? Would have been awful. Well, not awful, but okay. So does everybody see how that works? All right. Let's go to next topic now.
We're going to do that a lot?
We're going to do a few of these. Yeah. You have some homework problems to do with that are similar to this. Yeah. Now, the next topic that we want to do is, and this proof by mathematical induction is a really major topic in, it's a major proof technique in computer science. It's very important. So we're going to continue to do some more problems using proof by mathematical induction. And the next group of problems that we're going to do are proofs from definitions. Now, so let's take a look at this set of definitions that we have. 12.11 is the definition of b to the power n. And 12.12 is another definition of the same thing, b to the power n. And 12.13 is the definition of factorial. Now let's take a look at each one of these how many lines do we have in each one of these definitions? We have 2 lines. And what are the two parts of a proof by mathematical induction? A base case and a induction case. And in fact, these definitions are recursive definitions. It's defining something in terms of itself. Because see, let's take a look at 12.11. 12.11 says b to the 0 equals 1. That's like the base case. And then what is b to the n plus 1? Well, by definition, b to the n plus 1 is b times b to the n. You see what that is saying? So what that's saying is, 12.11 example here. 12.11 example. What this is saying is, suppose I asked you, what is 5 cubed? According to this definition, what is 5 cubed?
5 times 5 squared.
It's 5 times 5 squared. But wait a minute. What is 5 squared? It's 5 times, and 5 squared is what?
5 to the first.
5 times, yeah, 5 to the first. Wait, 5, oh, sorry. Sorry, yeah. This is 5 times, and then 5 squared is what? 5 times 5 to the first, right?
Right.
My 5's not very legible there.
What's that first?
5 times 5 to the first. But what is 5 to the first?
5 times 5
Yeah,
to the 0.
it's 5. So this is 5 times 5 times, and 5 to the first is 5 times 5 to the 0. Right? But what is 5 to the 0? Now we're at the base case, which is 5 to the 0 is 1. So this is 5 times 5 times 5 times 1.
That's stupid.
No, it's not stupid. It's recursive. It's a definite. You know what recursive? Have you guys done recursive?
Starting on.
Oh, are you starting recursion now?
And he's done a little bit of them.
Yeah, so a recursive function is a function that calls itself.
Yeah.
And this is a definition. What is the definition of b to the n plus 1? It's defined in terms of itself, b to the n. Yeah? So that's a, and 12.12 is another example, only this time instead of starting with n plus 1 and getting it in terms of n, it's doing what? Starting with n and getting it in terms of what? B to the n, n minus 1. So it's either way, they're equivalent. Either way, they're equivalent definitions. Either way, you're defining b to some power in terms of b to that what? One less power, right? And now let's take a look at the definition of factorial. You guys know what factorial means?
Yeah. Isn't it like 5 factorial is 5 times 4 times 3?
That's exactly right. Yeah, so 12.13 example. So what is 4 factorial? By definition, what is 4 factorial? What does it say there?
It's 4 times 4 minus 1 factorial.
It's 4 times,
4 minus 1.
yeah, 4 minus 1 factorial. So it's 4 times 3 factorial, right? But what is 3 factorial?
3 times 2 factorial.
3 times 2 factorial. But what's 2 factorial?
2 times 1 factorial.
But what is 1 factorial?
1 times 0 factorial.
But what is 0 factorial? Now we finally got to the what? To the base case. So that's 1. So this is 4 times 3 times 2 times 1 times 1. Is everybody, which happens to be 24.
Someone decided that 0 factorial is 1 just because? So that it would work with everything else?
Here's the answer to that question. The question was, why was 0 factorial defined to be 1? Here's my question. What is the operator here?
Multiplication.
Yes. And what is the identity of the multiplication?
Tricky.
Not, well, I mean, you understand, it's the identity element. Yeah? Okay. So here's what we're going to do. We are going to prove, so this is using, these are called inductive definitions. So, so here's how it works. Here's what we're going to prove. Prove that n factorial equals, now how would you write, now we're going to do some formal methods. How would you write that it's the product? What did you say n was? N times n minus 1 times, so what is, so what is that? That's the what?
Induction.
Is it the sum or the product?
It's product.
What's the symbol for product?
Multiplication.
Well, I know, but whenever we do quantitative, whenever we quantify it, what is it?
The dot. Wait.
No.
No, whenever we quantify it, what is it? Sigma is addition. Sigma is addition. Whenever you quantify multiplication, what's the symbol?
It's
Say it again.
zero.
Star? No, star is general. Star were those general ones, right? Oh, don't remember? What is?
Oh, yeah. It's pi.
Had to consult from outside. It's pi, right?
I was just saying whatever was thinking.
Is everybody good? Okay, so it's the product. Okay, so no, but we are now. Okay, and now, so it's product over what? What always goes here?
Dummy.
Yes. So any dummy?
Q.
I?
No, Q.
No, I. I is a common one. Yeah. Okay, so this product over I, range what?
N greater than 0.
No. N factorial. So it's, we want this to be, yes. Well, let's make it 1 and n. Okay. So this is 1 less than or equal to what? I. Less than or equal to n. So now what are the i's here? What are the possible i's here?
1 to n.
Gotcha.
1, 2, 3, 4, 5, and this is.
And we're going to do n minus
Why
I.
can't we do 0?
There's several ways to do this. Let's just do it this way. Yeah, that would work. Okay. But now body what?
N minus I.
No.
You sure?
Oh, actually, that would work, but there's an easier way to do it.
Easier than n minus I?
Yeah. No. Oh, definitely not n.
I'm confused. Tell me the easier way.
See if you can figure it out. What goes in the body here?
N minus 1.
No.
N minus I.
No. N minus I works, but there's an easier way. I.
What?
Yeah, because it's going up.
Because what are the possible, yeah, it's going up instead of down. What are the possible values of I here? What are the possible values of I in this range? 1, 2, 3, 4, 5, 6, up to n. And what are we doing with those? We're multiplying them all out altogether.
Those are integers.
Now, what you said was n minus I. Well, n minus I, if I goes from 1 to n minus I goes from n to 1 or to 0. Well, anyway,
Yeah.
whatever.
Which is more correctly represented.
Well, okay, hold on. For n greater than or equal to 0. For n greater than or equal to 0.
Base case.
No. Well, this says that our base case is going to be 0.
Yeah.
Base case.
All right.
In saying let's do it. Let's do the basic.
Okay, so now here's how this works. So yeah, first we do the base case. So now how do we do the base case? What do we always write down for the base? How do we do the base case? We write down the whole thing and then we substitute in for the base case. So base case, n factorial equals product over I, 1 less than or equal to I, less than or equal to n, body I, equals,
Base case is 0.
base case is n equals 0. So when we put n equals 0, what do we have here? 0 factorial equals the what? Product over I, 1 less than or equal to I, less than or equal to what? 0, body I, right?
So 12, 13.
Okay, so now this equals, by, let's work on the right side first. Now what is this? What is 1 less than or equal to I less than 0?
So
1 less than or equal to I less than or equal to 0 equals what?
False.
False.
Empty range.
So we use the ER rule, empty range rule. And what is the identity for product?
1.
And 1 is identity for product. So what do we get?
1 equals 1.
0 factorial equals 1. But now what about this 0 factorial?
12, 13.
12.13 equals by 12.13. 1 equals 1. Boom, we did the base case. Is everybody clear? Now, how about the inductive case? Now, here's the thing, you guys. The thing is, this, because we are using this definition, we can use textual substitution for this definition, right?
Yeah, let's put it in.
Okay. So now but now we have to write out our famous sentence.
Yeah.
Okay, so here's the inductive case.
Prove. Do we have to say must prove or to say prove?
Well, you can say prove. I like to say must prove, but those of you who like to abbreviate as much as possible.
What's up, Josh?
Yeah, not to mention any names, but we know you know who you are. Okay, that'll be funny because he's going to be watching this in the video. Okay, so must prove what?
n plus 1 factorial
Okay, n plus 1 factorial equals
N plus 1.
no,
Product over n
equals product over n. No, product over I.
is 1.
1 less than I.
Range 1 less than I less than n.
1 less than or equal to I, less than or equal to
N plus 1.
n plus 1, right?
I.
Body what?
I.
I, using
Using
Oh, yeah. Wait, no, isn't it a
N
semi?
factorial
using n factorial
equals
equals
product over I.
product over I, 1 less than or equal to I,
N
less than or equal to n,
I.
I, as the what? What do we call it?
Inductive hypothesis.
Inductive hypothesis. Now look, you guys, notice that you can't just take this and use textual substitution to prove this.
Right.
That would be trivial. I mean, that you can't do that. Why can't you do that? Because this is what we're trying to prove. You can only do textual substitution with a theorem. So we'd be assuming what we're trying to prove.
So we're not. Okay. Never mind. Let's just keep going.
But does everybody understand? This is what we have to prove, and we use this as the inductive hypothesis.
Right. We're gonna use the
How is
split
that
off
different
term.
than what we've been doing?
How's it? Yeah. How's it different?
It's not. It's proof by mathematical induction. Okay. But we're using.
You never made that note before, so.
I mean, we're going to use this though. We're using these definitions. Okay, so which side should we start? We want to prove this, right? Should we start with the left or the right?
The right.
Start with the right. So product over I, 1 less than or equal to I, less than or equal to n plus 1, body I. And what's always the first thing we do?
Write it out. Oh,
Yeah, we just wrote it out.
No,
Split
split
off
off
term.
term.
Split off term. Good. Split off term. And what term should, what are the possible, what's the last term here?
N plus 1.
It is n plus 1. And what's the
Multiply.
multiply? So how do you split off the last term here?
Times n plus 1.
So what do we write? Product
Product
over I.
Range 1
1
less than or equal to I less than n
equal.
plus 1. Or less
No, less than or equal to n body what? I times n plus 1. Is everybody clear on that? Now this equals by what?
Inductive hypothesis.
Inductive hypothesis.
And factorial.
Yes. So this is n factorial times what? N plus 1. Now, you guys, now, hold, yeah.
Which is 12. It's like 12, but sexual.
No, well, yeah, now how do we use 12.13? That's the question.
You replace, you
Oh,
use 12,
that is
you
it.
use the bottom of it. And
Yeah.
But the bottom of it has n factorial.
So check
But here we have n factorial times n plus 1. Here we have n times n minus 1 factorial.
same thing. Yeah, it's the same thing.
Is it?
Yeah.
How do you know?
The one that is one less is being factorial, and the one larger is
Okay, so basically it's 12.13 with what?
and replaced by a
Yes. And you can do that because that is a theorem, right? That's a definition. It's an axiom. Definitions are axioms, right? So you can do that with axioms. So let's do this. Let's say 12.13, I'm going to use a little slightly, with n replaced by n plus 1, which is, let's write it out. So what would that be? If we do 12.13 with n replaced by n plus 1, what would we have? We would have n plus 1 factorial, right?
Yes.
Equals what?
N plus 1
n plus 1 times,
n plus 1 minus 1 factorial.
yes, times n plus 1 minus 1 factorial, right? But this is n plus 1 times n factorial. There's n plus 1 times n factorial. And what does that say that's equal to? N plus 1 factorial. So this equals n plus 1 factorial, and boom, we're done. How's that?
boom, boom, bash, bash.
Bash, bash. No, that's not bash. Yes, it is. No.
Yes, it is. No, it isn't.
I thought bash was the back.
Here it is backslash is bash.
Backslash. Backslash is bash. This is forward slash. This is n plus 1 bang. Have you heard of that?
Yeah.
The bang is, yeah.
It's not.
N plus 1 bang. Boom, boom. Bang, boom, boom. See you next time.